Is there anything else from the homework anyone would like me to go over? What is that? Nice. Is there anything else anyone would like me to go over? Wow, brutal. Dana. Number 10. Yes. Okay, a 1,250 kilogram physics dragster is traveling at 35 kilometers per hour east when it hits the gas and accelerates at 12.5 meters per second squared for 3.25 seconds. What is its change in momentum? Okay, here we go. So, change in momentum. Momentum final minus momentum initial. So that's going to be mass times velocity final minus mass times velocity initial. We have a mass. I have an initial velocity. Watch your language, Kale. I don't know the final velocity. We have to go ahead and find that. So we're going to have to use kinematics to do that. The words are hard. VI is 35 kilometers per hour. So to take that and put that into meters per second, I'm going to divide by 3.6. And that's going to be something. 9.72. V final is what we're looking for. The acceleration we have is 12.5. And we know that it accelerates for 3.25 seconds. So then to find out what that final velocity is, we're going to plug it into VF equals VI plus AT. VI is 9.72 plus 12.5 times 3.25. This will give you the VF. You plug that guy in there, this guy in here, and M is 1,205, and you'll get a change in momentum of 49,000 kilogram meters per second. That's not the only way to do that, but that at this stage is the way I'd recommend for most of you to do it. Dana, does that make sense? Okay. There is a more elegant way to do it, but at this stage, the vast majority of you would be better off doing it that way. Okay, anybody else? Comments, questions, concerns, anything I assigned for homework? Is there anything here anyone would like to go over? Going once, twice, thrice, sold. Okay, cool, let's do it. Impulse, lesson 2 of momentum. Impulse is, what's impulse? What is your understanding of that word? A spontaneous act. All of a sudden you were doing nothing. You received the impulse and now you're doing something. So you can think of impulse as, I mean, in life, general life, not physics life, but in your world, an impulse is generally something that took you from a state of nothing and put you into a state of new. You're doing something you weren't doing before. In physics, I mean, you can think of impulse basically the same way. We're going to refine that definition just a little bit, but ultimately it's the same thing. Impulse is, in physics, it's a change in momentum. Just like in your life day-to-day, where an impulse is something that changes your state from not doing to now doing something. In physics, often it's a change from not having momentum to now you have momentum, or I had this momentum before and now I have this new momentum. They gave that, for whatever reason, I don't know why, but the language they've given to that idea of a change in momentum, they've called impulse. And so we calculated this yesterday already. You guys have found changes in momentum before. That was the question Dana asked. But I'm going to show you another way to do it. So we can derive the change in momentum from Newton's second law, which is originally actually where it came from. Newton's second law was not, when he originally published it, his second law was not F net equals ma. His original second law actually had to do with momentum, and then we tweaked it because it's easier to teach you guys F net equals ma and then then take it into momentum as opposed to the other way around. So Newton's second law starts here. We're going to go the other way. F net equals ma. But way back in kinematics, I gave you guys a definition for the acceleration of an object. Acceleration for an object was what? Way back, beginning of chapter 2. No, that was first lesson of chapter 3. Way back in chapter 2, what was the definition for an acceleration? Velocity, not just velocity over time, change in your velocity over time. Acceleration is a change in a velocity over time, which we can take this thing right here and just replace a for it. And I can say, okay, well, F net then is equal to a mass times a change in velocity divided by time. But I don't like denominators. We want to get rid of denominators. So I'm going to multiply both sides by time. And now we can see here that we've got an F net times the time is equal to a mass times a change in velocity, which is an expression that I gave you guys before. I just didn't really talk about it as being impulse, but it is. The impulse equation is this little dandy that I just gave to you here, and it is in fact on your formula sheet. It says that a net force times the time that net force is acting is going to be equal to the mass times the change in velocity. Well, and mass times the change in velocity, this is also just F net times time is equal to a change in momentum. Mass times the change in velocity is equal to the change in momentum. And so this is the impulse equation, and either side of this in isolation can be used to find the impulse in a given scenario. And I'll do a whole bunch of examples here now of why that is the way it is. And some really cool, I think really cool, sets of circumstances where this stuff's actually useful in everyday life. So, take a look at a couple examples. During an intense game of Smash Brothers, for those of you who never played Smash Brothers, I'm sorry for your life. It's lacking if you've never played Smash Brothers. Luigi, Mario's brother, swings a 9-kilogram hammer at Mario's head at 16 meters per second. Luckily, Mario's mustache brings it to a stop in 1/4 of a second, or 0.25 seconds. What is the net force exerted on the mustache? Well, okay. We're going to use, for the way this is worded, I mean, there's a few ways we could go about this. If I gave you this question, you could take a kinematics approach to this. You could say, okay, well, I know it was moving at 16. If it comes to a stop, now it's at 0. This is the time. I could find the acceleration. F net equals ma. I take the acceleration I find times 9 on the hammer, and now I have found the force exerted on the mustache. But this impulse equation now circumvents all of that. It's a way around breaking things up into kinematics and momentum. We can just say, okay, well, I know that F net times time is equal to a mass times a change in velocity. This is a relationship you want to hang on to. And so what this means is that F net times the time. How much time does it take to bring the hammer to a stop? Well, it's 0.25 seconds there. So F net times 0.25 is equal to 9 times the change in the velocity. Now, if you recall, change in means V final minus V initial. So the final speed of the hammer is 0 minus the initial speed of the hammer, 16. And now we've taken all of that and we've reduced it, instead of being a kinematics and then a dynamics problem, by bringing in momentum, we can get rid of all that. You can say, okay, well, F net is just going to be 9 times negative 16 divided by 0.25. What is the net force then on the mustache? And incidentally enough, Mario's face. As soon as you got a number, anybody. Hopefully your answer is negative. What's 9 times 16 times or divided by 0.25? Brad. Negative 576 newtons. Why is it negative? Yeah, so what this is the change in momentum of the hammer. And so this is the force exerted backwards on the hammer. Mario's mustache exerts a negative 576 newtons on the hammer. So what is the force exerted on the mustache then? If this is mustache on hammer, then hammer on mustache must be, yes, Colden, equal to and opposite, positive 576 newtons. Because this is what the mustache exerts on the hammer, equal to and opposite is going to be what the hammer exerts on the mustache. Cool. And now we can stop bringing in kinematics, at least for a little while. Let's do another one. I don't play soccer. So soccer players in the room, you got to tell me if this is legitimate. We've got a soccer player kicking a 450 gram or 0.45 kilogram ball at 25 meters per second. So that's just under 100 kilometers per hour. Is that a reasonable speed, soccer players? Okay, Marcus says yes. If the goalie stops the ball by exerting 250 newtons of force, how long does it take the ball to stop? Sorry, Kay? Okay. Too slow or too fast? I don't know. Okay, so here's what the question's asking. You've got a ball traveling at 25 meters per second. And I don't play a lot of soccer, but as far as my understanding goes, goalie usually wants to catch this in a set of gloves. Four fingers and a thumb. And he wants to catch this thing and bring it to a stop. But that doesn't happen instantly. Really what this question is asking is how long does it take once the ball begins to contact the hands? How much time does it take the goalie how much time does it take for the goalie to actually bring the ball from 25 down to 0? Is what the question is asking us to find. It's not instantaneous. This is another example of the impulse equation. So F net times the time is equal to a mass times a change in velocity. If velocities are changing and they give you forces and times, that's your clue that impulse is what needs to be brought in here. And it's going to take practice for you guys to recognize that. So we know that there's 215 newtons of force. We're looking for T. And that's going to equal 0.45 kilograms times a changing velocity. Change in velocity is what? It was moving 25, now it's moving 0. It's going to be negative 25. I have made an assumption here that's going to be problematic. What's the problem with what we've written here? As it stands right now, the time is going to be what? Negative. Can you have negative time? No. So what's the problem? How do I make it so that the time is not negative? Yeah. The assumption that I made was that when I called this 25 meters per second, to the right is positive. What direction is the force that stops the ball? It's got to be to the left. The ball's moving to the right and then it stops. So there has to be a force acting to the left. This is the force that they give us in the problem. The goalie stops the ball by exerting 250 newtons of force. So if that's to the left, this value actually needs to go into the impulse equation negative. So we're going to get negative 215 times time is going to equal 0.45 times negative 25. That's the same sign. So we're going to get a positive value for time. So the time then is just going to be 0.45 times negative 25 divided by negative 215. What is the time required to stop the ball? What is that number? It's going to be small. So in 5/100ths of a second, that ball is brought to a stop, which is reasonable. You guys don't, like, when you're watching sports or like football, soccer, it's not like the goalie stops and catches the ball and is dragged back a ways. Usually the hands go up, the ball hits, and it's done. Maybe it deflects off, but maybe it's just brought to a stop as it's being caught. That's entirely reasonable. The point being, it's not zero. It's never zero. Nothing can happen instantaneously. What if instead it's not a soccer player kicking a 1-pound ball? What if it's that same goalie stopping a 6.5 kilogram bowling ball shot out of a cannon? I'm going to change it. I want to say, let's say he's stopping it with the same time. How much force is required to stop it? A bowling ball is being shot out of a cannon at the goalie, and the goalie is going to stop the bowling ball the same way he or she stopped the soccer ball. What is the force required to stop the ball? So here we go. Momentum question, F delta T equals M delta V. Now, instead of finding time, now we want to find force. What is the goalie going to have to exert this time to stop it with the same amount of time? So this is the time we're going to use down here. We're going to have F times 0.05 equals, now it's a 6.5 kilogram ball being stopped in the same way from 25 meters per second down to 0. If we want to solve this thing for the force, it's going to be negative again. That's okay. Forces are allowed to be negative. It just means it's backwards against the direction the bowling ball was coming from, which is what you'd hope. You want it to be backwards against the initial path of the ball. So how much force does our goalie have to exert now? Negative 3,250 newtons of force. Substantially more. To put it in perspective, it would feel like exerting 3,250. That's equivalent to 330 kilograms of mass. Like, that's being lifted. Like, that's an absurd amount of force required to stop this ball. Which leads us into why the impulse equation is so useful. Take a look at what we've done here. What would we, again, so the scenario on the right-hand side stays the same. I have a 6.5 kilogram bowling ball. I'm bringing it from 25 meters per second down to 0. how could I decrease, looking at the math, how could I decrease the force required? How can I make that F value smaller? By increasing the time. If this time value goes up, this value for the force goes down. Is the really kind of the key part with this impulse equation. And there are so many examples of this in the real world. One example of this is this. When you guys jump, for those of you who play sports, or maybe you're doing something stupid in class and you're up on, I leave the room to go fill my water bottle, and for whatever reason, Colden decides it's a good idea to get on his desk. I walk through the door. He realizes he's not supposed to be there, so he immediately jumps off the desk in hopes that I don't notice. I've been in that classroom. Not Colden, obviously, but we're picking on Colden today. If you're going to land at this stage in your guys' life, you should recognize that bending the knee on impact prevents a ton of damage to your knees. There is a proper way to land. If you lock your knees and just hit the ground, the chance of you seriously hurting yourself is really high. Why? Brad?
You're kind of like going with the flow more when you like bend your knees, because you're going with they're like going down with like the gravity pulling you down, whereas like giving your legs locked, they're just kind of reacting their own way. It's kind of like inertia, isn't it?
Kind of.
Yeah.
Kind of. It's a cushion to your body weight. So I'm going to do something I probably shouldn't do, and I'm going to demonstrate what Colden was doing. What we were imagining Colden. Okay. So I'm not gonna jump from there straight leg because I will seriously hurt myself. But look at the difference between something like this. If I jump up, lock my knees, I can't even do it. If I lock my knees, even that hurts. The stop is quick. It's jarring on the whole body, the stop is quick. If I get up on a chair and I drop, the inertia of the rest of me is going to make my knees buckle. If I do it in kind of a controlled way, instead of hitting the ground and immediately coming to a stop, I allow the rest of me to slow down by bending the knee. And what I'm doing is I'm increasing the time, like Kai said, and increasing the time decreases the force on any one part of me as I bring all of me to a stop. Do we do this? Yeah, we do. I'll show you, mathematically, I'll show you what I mean here. Okay, so let's say you have a student with a mass of 65 kilograms, and they're going to drop from a height of 1 meter. Their displacement is going to be -1 meter because they're dropping 1 meter. The initial velocity is 0. They're just stepping off the chair like I just did. Their acceleration is going to be -9.8 meters per second squared. What's the final velocity of that person as they hit the ground? Dropping 1 meter. So 1 meter is a little bit taller than your desk. To drop that, I'll do the equation for you because that's not what this unit's about. VF squared equals VI squared plus 2AD. So VF, if I plug all of these things in here, that's going to be gone. It's going to be the square root of 2 times 1 times 9.8. The final velocity here is going to be 4.43 meters per second. So let's say we have a 65 kilogram. You know what? Forget 65 kilograms. Let's make it mean. Let's make it 100 kilograms. You got a 220-pound dude or a 100-kilogram dude dropping 1 meter. The final velocity is going to be the same. And we're going to, now to stop this 100-kilogram dude, we need to bring that down to 0. So what is the force required if the knees are locked? If Fnet times time equals m delta v, and I lock the knees. The time is short. Maybe it's 1/10 of a second. Let's say that time is 1/10 of a second. 0.1. Well, the force then is going to be, if I divide time over, it's going to be the mass of the dropped person times the change in velocity, negative 4.43, because it was 4.43 down to 0, divided by 0.1. These numbers are nice because dividing by 0.1 is the same thing as multiplying by 10. So multiplying by 10 and multiplying by 100, I'm just going to add 3 zeros to this. It's going to go over 1, 2, 3. The force required to stop me with the knees locked is 4,430 newtons on the knees. That is bad. What if I gave myself time to stop? What if I allowed the knees to bend? What if I gave myself, instead of 1/10 of a second, what if I increased it to 1/2 a second? What if instead time was allowed to be 0.5? The math stays the same, except that time increases, divided by 0.5. If I plug those numbers into the calculator, 100 times 4.43 divided by 0.5, now instead of 4,430 newtons, by going from 1/10 of a second to 1/2 a second, that number drops down to 886 newtons. 20% of what it was to start. And all I've done is allowed myself an extra 4/10 of a second to stop. Not a lot of time, but massive as far as what it does to save the body. 4/10 of a second is not a lot of time, but the savings are huge. 80% less force. And so we apply this all over the place. One of the applications for this is in cars, all over the place with cars. What are some of the ways we extend the impact time for a car in a car accident? If you've never been in a car accident, if you've never seen a car accident, consider yourself lucky. The airbag is one. So your inertia, you're moving forward, the car comes to a stop around you and you keep going. If the airbag is not present, what's going to stop your face? The dashboard or the steering wheel? Rigid surface, it's going to take not much time at all for the dashboard to say, cool, your face is no longer moving. But instead, Kai mentioned the airbags. What do the airbags do? The airbags, as soon as the car feels an impact above a certain threshold, an explosive goes off inside your dashboard, inflating that airbag before your face has a chance to get to where it is. So now you've got a big pillow full of air. And I think it's actually nitrogen, but that's okay. So now it's in your face, and it gently brings you to a stop, and it's the act of you hitting it that deflates this thing. Increasing the amount of time that you come to a stop, decreasing the force on your face. Kai also mentioned seatbelts. Seatbelts do the exact same thing. Instead of the dashboard bringing your whole body and the windshield bringing your whole body to a stop, the seatbelt has a little bit of give, increase, even by giving you an extra fraction of a second, you massively decrease the force on the body. It's this one down here too. Conventional wisdom suggests that cars should be made of tough and rigid to prevent injury during a collision. This is how cars were built in the 50s and 60s. If you have a car from the 50s and 60s, they are solid. There is no give. If you hit something in one of those, the car will probably be fine, and whatever you hit is going to pay for it dearly. Nowadays, cars are built of plastics and fiberglass, and they crumple to nothing. What's the purpose of that? Why? You would think that perhaps a more rigid car would save the people inside, perhaps, maybe, I don't know. That was the conventional wisdom of the time. Why the crumple zones? Brad? It's the same idea. It increases the time. It brings you to a stop. Between it and the airbag and the seatbelt, the occupants of the car that is being crumpled is surviving, and it decreases the amount of time on the other vehicle. By having your car crumple, you're more safe inside that thing, and the other people that you just hit or who hit you are also safer. If you increase the time to stop, you decrease the force required. And the application of that is all over the place. It's the same thing with the airbag. The principle of impulse. Explain why an airbag can help people sustain less damage during a collision. It's the same thing. You're increasing the amount of time it takes your face to come to a stop, which reduces the force on your face. It's the same thing with boxing gloves. If you've ever punched something, or if you've ever been punched or slapped barehanded versus with a boxing glove, the boxing glove is still pretty hard. But again, even a little bit of extra time, a little bit of cushion, decreases the damage on the face. I don't know a lot of people who go multiple rounds bare knuckle boxing. You can't. The body cannot survive multiple rounds of bare knuckle boxing. But the amount of guys that go 10 rounds in the ring, beating the snot out of each other with gloves on, because the body can sustain that, and then it's more entertaining to your spectators. No one just died. And you got to see a full 10 rounds of a fight, perhaps. The gloves increase the time the same way an airbag does in the car. The opposite is true in other sports. Baseball, golf, hockey, basketball. I don't know how many coaches I've had in how many different sports that all said follow through. What does follow through do? So let's say you're a baseball player. You're playing baseball, and or a golfer. Golf is actually probably a better example. Because with golf, the technique, from what I understand, is you want to swing the club not to hit the ball, but to go all the way around. Like, you want to make sure that that swing goes all the way around you. The twist needs to go so the club started behind and ends behind. What does that, that's what follow through is. Why is that important? If it was just to hit the ball, maybe you stop the club as the club hits the ball. Let's take a look at the impulse equation and analyze why this is better. For argument's sake, let's say that you're able, the force doesn't change. The amount of force that you're exerting remains constant. Whether you hit the ball and stop the club immediately, or whether you hit the ball all the way through, let's say the force is the same. The mass of the ball doesn't change either. This is a constant. This guy here is V final minus V initial. What does follow through do to this value right here? By following through, your club will have a chunk of time or in baseball too, the bat will have a chunk of time where it is moving with the object you just hit, whether it's the golf ball or the baseball. So by following through, what you're doing is you're taking the time of impact and you're actually increasing it. Not only is the ball being hit by the club or the ball being hit by the bat, but for a moment of time, the ball and the bat get carried together. The club and the bat get carried together. And so you're doing is by following through, you increase this time. If the force is the same, the mass is the same, and this value goes up, what does that do to your change in velocity? If this stays the same, and this stays the same, and this goes up, then this guy has to do what? They're on opposite sides of the equal sign. If these two are the same and this one goes up, it has to. The force you're exerting hasn't changed, but even just a little bit more time in contact, this V final shoots through the roof. Something as simple as your coach telling you to follow through has profound mathematical implications. That final velocity is going to be so much bigger. It's why same thing with if you're fighting. If you're in a fighting sport, boxing, MMA, martial arts, and you're striking, correct me if I'm wrong, Lachlan, you're a boxer, yeah? Lachlan, you're a boxer? Is your goal to hit someone's face or to punch through their face? You want to punch through the face. Why are you punching through the face? Because you're increasing the time. You don't want to slow down. It's increasing the damage you're doing to the object. In the case of baseball, you want to damage the baseball. You want to damage the golf ball. You want to damage the other person's face if you're boxing. Follow through is important. Okay, one more example. Where are we here? There we go. The TL class super tanker is the largest kind of ship in the world. When fully loaded, it has a mass of 509,000 tons, which is 509 million kilograms. And it can cruise at 31 kilometers per hour. In the event of an emergency, the crew can perform what's called a crash stop. Any ships can do this, aircraft carriers can do this, tankers will do this, cargo ships will do this. And what a crash stop is the engines you don't just put on the brakes in a boat. If you want to stop in a boat and you just cut the engines, you're going to float for a while. So what they do is they cut the engines and then put them full throttle in reverse, which is something we don't typically do in a car. If that's how you stopped a car, what would happen to the transmission? It would probably explode out the bottom of your car. In a car, we use brakes. Boats don't have brakes. Boats, you got to put the engine in reverse. So the engines on that thing can generate that's a relatively staggering number. 5.22 times 10 to the 6 is 5, followed by 1, 2, 3, 4, 5, 6, 2, 2. That's going to be a 0, a 0, a 0, and a 0. Newtons. No, did I miss a 0? 1, 2, 3, 4, 5, 6. No, we're good. So that number, just so we're clear, is 5,220,000 newtons. That is a ridiculous amount of force. How long does it take to stop the ship? This is the fastest possible way to bring this super tanker to a stop. Well, let's write everything down that we know. The mass is 509,000 tons. Add 3 more zeros to turn it into kilograms. The initial velocity of this super tanker is 31 kilometers per hour, which I'll do the conversion for you. You divide by 3.6, and that gives you an initial velocity of 8.61 meters per second. The force produced by the engines is 5,220,000 newtons. How long does it take to stop the ship? Well, the impulse equation relates these, and VF is going to be 0 to bring the thing to a stop. The impulse equation is the equation that relates these concepts together. F net times the time equals the mass times the change in velocity. Now the force is acting against the ship, so it's going to go in there as a negative value. So we have a force of negative 5,220,000 times T. The mass of the ship, 509 million kilograms. And the change in velocity is going to be negative 8.61. Final velocity is 0, initial velocity is 8.61. So delta V is going to be negative. How much time does that take? What is 509 million times 8.61 divided by 5,220,000? What's the value there to stop the ship? Someone who's got a calculator. Anybody? Ezra, you got a number? 839, and the units on that are what? Seconds. So 839 seconds doesn't mean a whole lot, so let's turn that into a meaningful value. Let's turn it into minutes by dividing by 60. What's that number, Ezra, divided by 60? So effectively 14 minutes. So at its fastest, at its shortest amount of time, that tanker is going to take 14 minutes to come to a stop. To put that length of time into perspective, and that's in an emergency. It doesn't get any shorter than that. To put that amount of time into perspective, because when's the last time we measured out 14 minutes? I'm just going to do this and let this sit here. We've put the engines in full reverse, and they are going to be in full reverse until this reaches 0. While we're waiting for that to happen, this is the end of impulse. That's my lesson for you guys. I'm hoping you're seeing the value here. It's always a little bit weird when I get super excited and you guys are falling asleep. I'd like you to take a look at these 9 questions. I want you to do all of them. This is the homework for today. Change in momentum is called impulse. Really quite a useful concept. On your markets, go.